science, folks, you awesome, awesome environmentalists, chemists, biologists, whatever you want to be in the future. Again, this is Coach Powers with Science with Coach Powers. And we're going to get right into it. We have, of course, our presentation on your Unit 2. Okay, so I'm going to go ahead and present that as I fumble around with my mouse. So therein lies the presentation. It says Unit 2, the flow of energy. Right now, in the middle of the day, my flow of energy is transforming into other energy outside of my potential or body, as that way may. So we're going to look for more energy. 2.2 is your first technical section. Okay, it's called the flow of energy lesson. So what do we mean? We all know what energy means, the amount of it, but what do we define the energies in a science transformation, I guess, of lack of a better term? The flow of energy lesson states that the flow of energy lesson objectives in this unit, you're going to learn how to, well, define what is energy. I can define forms of energy. I can understand and design or create energy transformations. I can understand or I'll learn how to figure out how energy sinks and sources and energy resources. And that's the non renewable versus the renewable discussion I'm sure you've had for a very long time in your academic careers, to include this one as well. So, moving right along, continues. Energy. Well, how do we define that or part of that? Energy is the ability to do work. Okay, all living things require energy for survival. So does non-living things, as far as being able to work for living things. All objects in motion require energy for that motion. Okay, so having just said that, I'm going to do my little laser pointer so it makes more sense. Um, Energy is essential to the biological and physical world around us. Energy comes in many different forms. Okay, so what are those forms that we're going to study? Can you name them off the top of your head? I'm going to pause and let you do that. No, that wasn't a pause. That was actually me just standing still. Don't check your YouTube. So, potential energy and gravitational potential energy. You'll see these denoted in variables as PE and GPE. Okay, gravitational potential energy has a constant on this planet, 9.8 times 10 to the, I believe 10. Anyway, meters per second squared. Kinetic energy, energy of motion. Chemical energy, well, things we drink or use to start fires or things like that. Thermal energy, that means heat energy. Sound energy, that means, the sounds that are coming out of my mouth. I apologize, but my sound doesn't sound that good to the ears. And electrical energy, okay, things that we use to, charge our phones. The flow of electrons, basically, that's electrical energy. Okay, potential and gravitational potential energy. Wow. Okay. So what does that? I mean, what does that mean? You have this diagram over here. Okay, and this diagram states that this car's on the top of the hill. Okay, it's just sitting there technically because look, the wheels aren't even on the ground, but it has the potential to go downhill and start to move. So that's potential to go downhill, and then when it's moving, it becomes kinetic. Okay. It takes a lot of energy to get higher potential energy up the hill. Then as we go down, potential energy goes lower. Okay. So let's read what this says. Potential energy is the energy that is stored and can potentially be transferred into another form. A specific type of potential energy, gravitational potential energy, results from the height of an object above the ground level. Okay, so gravitational potential energy is a measure of how much potential movement and speed of the object that could experience if it were to fall. So if I were to take this and measure this level all the way up to this level, okay, maybe that'll be 20 meters high, which it's kind of big. That's 20 meters. That's the height. Gravitational potential energy is 9.8 times 10 to a power meters per second squared. And you'll have this going on as far as how much potential energy. MGH is the calculation, mass times gravitational potential energy constant. No, gravitational acceleration constant and height. So that actually it kind of will look like this. If you want to just write down GPE, I don't think you're doing calculations. Wow, look at that handwriting. It's magnificent. Okay, so you do have the mass times the gravitational acceleration constant times the height to calculate that actually. So as we go down this point here, we have different levels. Let's say it's point A, point B, and all the way down to, let's say, E, if I can do my thing. So where is the potential energy lowest? It's going to be at the bottom at E, and then the highest is going to be A, of course. Okay. So that's kind of the idea. Now, the next one is kinetic energy. So you'd have to pick out where is the kinetic energy the highest. And while I don't want evidence of this going up, and being around as far as my handwriting is concerned, that's I'll take that evidence away. But you can screenshot that when and say, look at Coach Powers' handwriting. So now let's look at kinetic energy. Okay, it's the energy of movement. Okay, any object in motion is showing kinetic energy. It's directly related to gravitational potential energy. The larger an object or the higher the object is above the ground, the more kinetic energy it has. Uh, well, deceivingly, that is a good definition. But as we said here, if this is really high, the kinetic energy at the middle here is going to be really a lot more if it were a lower potential energy at this level, based on this, calculation where the height is getting lower, mass stays the same, this stays the same, but the GPE is getting, if the GPE is really high, the kinetic energy has a chance to be high as well. And you notice this is similar to that diagram, although there is basically zero kinetic energy here, larger kinetic energy here, and when it hits the ground, your GPE is potentially zero and also potentially zero at kinetic energy. Okay, so kinetic energy movement, any object in motion, basically. Okay, moving right along. Other types of energy, you have chemical energy. This is chemical energy that is stored in bonds between the molecules of a substance. Anytime a fuel or food source is used, chemical energy is being released and transformed. Okay, it's a strange representation here, but what they're trying to say is there's some chemicals, okay, that are in a substance. Let's say it's a lighter fluid, like an igniter type of a fluid. It's that chemical energy is, using heat, breaking up bonds, and allowing flames to go faster as a catalyst. You eat food, it breaks down the bonds between carbon bonds and carbohydrates and lipids and things like that. If that actually gets digested at some point in your stomach, you're and releasing energy in the form of ATP and other types of energy formats. Thermal energy is often referred to as heat energy. Thermal energy is released in three different ways. Okay, so you see the diagram over here. Okay, conduction is heat transferred when two objects touch. Okay, convection. So we have two objects touching. So this metal rod over here is touching the heat and it's conducting the heat up the metal rod. If it is actually a metal rod, it's hard to tell from that diagram. So convection now. Well, what is convection? You see the hands up here, heat source down here, and convecting up to the hands. Okay, so heat is transferred as warmer gas or liquid molecules rise away from the heat source and cooler molecules sink toward the heat source. So actually we get this convection up and cooler going down, okay, toward the heat source getting reheated. Okay, now the last term here is radiation. Okay, heat is transferred around particles, thus allowing heat to move through open space. Okay, so it's basically a nondescript area um, around particles, allowing heat to move in open space. So radioactive stuff goes to open space and tends to disperse through that. Okay, so I'll get you through that section. Let's go different color laser pointer. That'd be cool, wouldn't it? I like messing around with that stuff. Let's go below. All right. All right, so I'm just having fun there. I'm just going back to my laser pointer. It's just even more fun for me. All right, so sound energy. My sound, as I get less and less of energy, might sound worse. The picture does look bad already, but sound energy moves in waves through the air. The sound source causes vibrations. So we have a source, looks like a speaker, and you got the wave here, and of amplitude. You have wavelength. You have the crest and the trough, and you're getting some sound waves. All right. Basically the sound causes vibrations in the air, pushing the air molecules against the eardrum of the listener. This causes the eardrum to vibrate, which can be perceived as sound. So that is kind of the force that's generated by those waves. And then electrical energy, you'll see this right here on the bottom. An example: electrical energy occurs when electrons move in a current through a wire. That represents a wire. If you guys have seen that before, connecting things and twisting and making lights work. It only takes myself to put in a light bulb sometimes. All right, so law of conservation of energy. This is what we talked about. If you talk about hypothesis versus theory versus law, the law of conservation of energy states that energy can never be created nor destroyed. Well, wait. I mean, what if a battery gets low and that chemical battery acid isn't working anymore? And doesn't that go away? Well, it's transferred into different forms. It's still there somewhere. Okay, this has been proven repeatedly in scientific experiments. Energy is transformed from one form to another, but never created nor destroyed. A good example is a transformation of GPE to KE in the image below. Ball's not moving at the top, okay, of the cliff. Well, and it has a lot of potential energy because of its height above the ground, but it has no kinetic energy. It's not moving. Okay, it's at the top. It has the potential to move very fast if you drop that thing, and the gravitational acceleration constant will act upon it. Um, but it has no kinetic. And when the girl releases the ball, the potential energy decreases as the ball gets closer to the ground. However, the kinetic energy increases as the ball speeds up. So it's almost like an inverse relationship. All right, the flow of energy lesson continues. In this scenario, you can clearly see how energy is transformed, not created nor destroyed. And when it goes to the bottom here, you might have basically some release of energy of no potential and no kinetic if it stops, but it still has some forces that can act upon it. Okay. All right. So as we seek to use energy forms in the environment to provide the energy we need for our homes and societies, we have to be aware of sinks and sources, similar to the sinks and sources we discussed in the biogeochemical cycles in Unit 1. The carbon sinks and sources exist for energy. An energy source is called a resource. Okay, it provides us with usable energy. All right, energy sources are accessible and attainable. Okay, a sink, we heard this before, an energy sink occurs when the energy is no longer accessible and attainable. For example, biomass, which is technically plants. You can use corn for ethanol. Biomass on the deep ocean floor is not attainable to us, so it's considered a energy sink. There's nothing being used there. Okay. Um, the energy will remain in its stored potential chemical form until it can be accessed and transformed. Now, that's something we're trying to do in the future more and more if you learn about the future of the ocean exploration and usage. And that is 2.2, and we're moving on to 2.3. So having said that, I'm gonna allow you to either stop this video and go back, take more notes, answer the questions for this section, and we will hopefully move on to 2.3. Okay, 2.3 forms of energy. Okay, let's go to the presentation and see if we can knock this out. A lot of repetition or some repetition, which is good because it becomes more accessible in your brain. It doesn't take a lot of energy to bring it up. So 2.3 forms of energy. Um, well, we have these forms, and the energy, as we said, is the ability to do work. Sometimes that is basically a repetition, but the various forms is kinetic, sound, thermal, chemical, electrical, and gravitational energy. There's some other ones as well that we'll possibly get into. All right, so kinetic energy is the energy of an object due to its motion. All moving things have kinetic energy, including large things like even planets and small things like atoms. The heavier a thing is, and the faster it moves, the more kinetic energy it has. Mass is I'm seeing one half the mass times the velocity squared is that. Wow, that's a review from the past, isn't it? For those that took, you know, what this is kinetic energy. Watch this. Look at that handwriting. Unbelievably good. I don't know how they do that in Khan Academy. I need a better mouse probably. So it's one half, okay, mass times velocity squared. So those that want to see it mathematically might be able to understand it better. So as a mass goes up, your kinetic energy can go up. So mass and velocity, the speed at which it's going, goes up. That generally goes up too. So now that's the mathematical representation. I should never write, but that's just the way it is. Let's quickly erase that before someone sees me. All right, no, they all see me. I guess it's recorded. The evidence is here. All right, so both of these balls are on the table above, basically they're above the table. They have potential energy while resting on the table. PE or potential energy refers to stored energy. They also have the gravitational potential energy on the high table. Gravitational potential energy is the stored energy an object has due to its height. If the balls were to fall off the table, potential energy and gravitational potential energy would change to kinetic. It sounds very basic. Hopefully, that is drilled in. Now, let's talk about sound energy, a little bit different off the path here. So, sound is the movement of energy through substances in longitudinal waves. Okay, not unlike the waves you see in the ocean as far as power, frequency, and things like that. Wavelength, how between the two waves, the period. Waves that move back and forth. Sound is produced when a force causes an object or substance to vibrate. The energy is transferred through the substance in the wave. Okay. So there is a medium a wave can travel through. All right. So when someone plays a guitar, which I'm going to because I might have to record this, the strings vibrate and transmit kinetic energy. It's movement of something. The kinetic energy from the moving air molecules transfers to sound energy to the listeners in the room. Okay. Hey, here's the one we see a lot in science: a thermal energy or heat energy. It comes from heat. A cup of coffee. This coffee is brought to you by coffee and brought to me by the mug that, I don't have any new jokes right now because teachers have no sense of humor that we know of. No, I don't. Most teachers do. There's some funny ones out there. Basically, thermal energy, a cup of hot coffee is thermal energy in the form of kinetic from its particles. Okay. Some of this energy is transferred to the particles in cold milk, which you pour to make your coffee cooler. I just do it because, some people just do it. I don't do it. You drink black coffee, but, it's other reasons people do that. Thermal energy is the energy that causes objects to gain temperature. Let's take a look at an example to see the difference between heat and temperature. Okay, so we have a swimming pool. I'm not going to draw that at 30 degrees Celsius. Okay, imagine what that's about 75, between 75 and 80 degrees Fahrenheit, has a lower temperature than a cup of coffee. However, because the swimming pool contains more water, it stores more thermal energy than the cup of coffee. So we're looking at volume here. If there's a lot of volume in something, even though it's a lower temp technically, there's a lot more stored energy that can be given off in that little teeny cup of coffee over time and spread out. Okay, heat can be transferred from particle to particle or object to object in three different ways: conduction, convection, and radiation, which we saw an example of that in 2.2. All right, conduction, a better definition of this. When a substance is heated directly, its particles gain energy and vibrate more energetically. The particles bump into nearby particles and make them vibrate more. This passes the thermal energy through the substance by conduction from the hot end to the cold end. Well, think about that. We will talk about solids, liquids, and gases. A solid, like an iron poker, as we saw in that diagram, will touch the heat, become hotter, and the heat will be transferred up the metal rod. And basically, molecules and particles are moving more and transferring this energy. Um, Good examples of insulators are air and plastics. Okay, so that's a good one. Conductors are metal. That's a good conductor. Right. When particles, this is convection now, a different one. So don't get those two. D and V are different ones. Particles in liquids and gases get warm. They become less dense and rise. The space is quickly replaced by cooler particles and are less dense because they are heavier. Thermal energy is transferred from hot places to cold places by convection. It's almost like it's diffusing from a high concentration of heat to a low concentration of heat. It convects. It convects. Right? So it's almost like creating a vacuum of from hot air moving to then the cold air moves in to that area. Okay, radiation. We all know about radiation. There's UV radiation. They tell you your phone is emitting microwaves radiation in your ear and surrounding parts. All objects transfer thermal energy by infrared radiation. Okay. The hotter an object is, the more infrared radiation it gives off. No particles are involved in radiation, which means the thermal energy transferred by radiation can work in space, but conduction and convection cannot. Okay, there has to be a definite closeness to the source. Now, chemical energy. Okay, I'll give more examples of radiation, but here we go with chemical energy. Right? The energy stored in the bonds of atoms and molecules, it's chemical energy. Right? So if you have a molecule of, let's say, carbon dioxide or a carbohydrate, sugar, C6H12O6, you have six carbons with six bonds between carbons. I'm sorry, the six carbons. You have, they are capable of four bonds each. And if they break, they release the energy. It's potential energy when they're stored in the bonds. Okay, most examples of stored chemical energy include batteries, biomass like plants, petroleum, natural gas, and coal. When explosives go off, the stored chemical energy inside gets transferred to the surroundings as thermal and sound and kinetic. Okay, dry wood also has stored chemical energy. When the wood burns in the fireplace, chemical energy is released and converted to thermal and light energy. Think about that. You see it as light and it's hot. So we have some transference of different forms. And now let's talk about electrical energy. Right. So all electricity is it's the flow of electrons or negative particles through wire. Okay, batteries transfer stored chemical energy when charged particles called electrons move through the wire. All right, electrical energy is transferred to its surroundings by a lamp in the form of light energy. An example of electrical energy in the nature is lightning. In nature is lightning. So positive to negative flow or negative to positive flow. Lightning is so powerful that it isn't confined to a wire, even though we think that, Benjamin Franklin, captured lightning. Now, it just was a conduction of the electrons from a source, an electrical source, but or else he would probably not have been able to move on past that. Also, gravitational energy. Guess what? We're feeling energy all the time. A rock on a mountain has stored energy. We've seen this before. If it's high, it has higher potential energy and a potential to do more kinetic energy or greater kinetic energy. Sorry. The energy stored in an object's height. Okay. If the rock falls from the mountain to the ground, gravitational potential energy gets transferred to kinetic energy. Now, keep in mind that there is a difference between potential energy and gravitational energy. Potential energy is stored energy, whereas gravitational energy is the energy only stored in the height of the object. Okay, so gravitational energy, height of the object comes into play. Right. Part two of this energy transfer, very short. So look at these examples over here. Okay, we have chemical transferring to light. We have chemical into mechanical. Chemical into mechanical. The body's a machine, basically. Electrical, flow of electrons into a light source. And electrical to heat. Light to chemical. See how these things work? The law of conservation of energy states that energy can never be created nor destroyed. Instead, energy is transformed from one form to another. Now, this is not a full diagram of all the possibles. You still have radiation that could transfer into something else, like mechanical, just like we're trying to do with Duke Power in our nuclear plants, radiating that kind of energy. So we have a nuclear energy. We have all kinds of different forms that we haven't talked about, and I'll try to give examples. And that concludes 2.3. We're getting into 2.4 energy transformations. So that is going to be coming up. And enjoy Rock Week if you can. This might be another week based on the timing of this, but enjoy. We'll see you in a second. Okay, we're back and we're going to look at 2.4 energy transformations. I hope you guys taking good notes for the test coming up. We're going to look at this and see if we can grasp how energy does transform. So when it does transform, we're looking at how it does. So again, more examples of chemical. There's some chemicals in that ice cream cone, and it can get to kinetic when we use that energy and break it down. Has the potential to move based on the chemical energy provided and the bonds between the molecules. Light energy from the sun creates the photosynthetic energy into a chemical process. So you know that there's a light and dark reaction in photosynthesis, creating ATP molecules, which is used for energy and those kind of things. And this transformation of energy video is in Virtual SC. If you want to go and look at that in section 2.4 in Unit 2 in your 2.4, right? So energy is basically changing. Okay, it goes from one form to another, and it's called energy transformation. Of course, and you take every second of every day, uh, and basically there are many different forms which we saw. So watch the energy transformation video to learn about different forms of energy to see examples. So I'm not going to have a video within a video. You know how I love to do that. So go ahead and watch that video when you can, and maybe take more notes on that, and may become more clear to you. Okay. Now, hopefully, with your study guide and review of this video, or of actually the sections in Virtual SC, and you've answered the questions in each section, which may resemble, if not be exact, to the test questions. So now you're going to take the Unit 2 test and scheduled in your calendar that's prepared for you. I contains links to that. So good luck to you on that. Hopefully you got something out of this. If you need some more help, there's office hours and you can come to those. So guys, great job. Take care. Live simply, care deeply, and love generously. And enjoy the week. Take care. Hello, science folks. You awesome. Ball game.